Hello everyone. So today we're going to continue on 14.7. So if I remember correctly, our last video I get to show you an example on how to use power series to form a solution. So once again, this particular differential equation y prime plus y equal to 0 would not require you to use a power series to do that, because as I say, characteristic root would allow you to solve this differential equation in about 12 seconds. I think it took me less than 12 seconds to actually write out the solution. So once again, I'm trying to use something simple like this to kind of illustrate to you the process of using power series and point out some of the important things you have to watch out for. So number one is to know this is what the power series solution look like, which is in this box. Notice what happens when you take the derivative of it, you have to change the index from 0 to 1 because the first term go away in the differentiation, and then re-index it. And one of the only reason why you re-index it is because you want it to be x to the k power. So later on we'll see an example where that is not necessary, and I'll explain to you why it's not necessary. Okay. And once you do that, you can now rewrite your differential equation into the power series by substituting y prime and y double prime, which in this example, I actually wrote these two things backward. I should have the y prime, which is this second term here in the front, but because of addition, so it doesn't really matter. And set equal to 0 in this case because we have a homogeneous differential equation. And if you do write out all the terms, you find out that you can actually combine the term together by simply combining the coefficient in front together. And that's allow you to do that because both of your summation have x to the k. If you don't have that, that would be where you would find it difficult when you try to combine multiple summation together. So that is something that you want to do so you can kind of preempt the issue and allow you to move into the next step easier. And once you've done that, you'll now be able to find a way to define the coefficient. Most likely in the scenario where you have a homogeneous solution, you just basically set the coefficient equal to 0. Because that's what a homogeneous solution is when the entire differential equation equal to 0, that means a power series with 0 coefficient for every single term. And once you do that, then you can then form a recursive formula and use that recursive formula to try to find C sub k. And in our case, our C sub k is actually very easy, and we actually would be able to transform our summation into a closed function form, C sub 0 e to negative x. Now, does that always happen? No, a lot of the problem that we're doing would not have a nice simple solution like this. Reason, if our differential equation actually have a nice simple solution like this, that means there are other methods that will allow me to find that nice solution. Okay, we're only learning using power series solution because we are solving a differential equation that cannot be solved any other way. That's the reason. So show you another example similar to this one. So this one, once again, you will not use power series to solve, but I'm using it to illustrate, the process, of course. Given y double prime plus y equal to 0, solve using a power series solution. Now, once again, this one actually also extremely easy. So once again, I'm going to give you, this one maybe take about 20 seconds to figure it out. So I'm going to give you 20 seconds to try to find the solution to this differential equation. It is almost as simple as the last one that we did. Okay, so 20 seconds starting right now. Okay, that's it, 20 seconds. Hopefully you have a solution already. So I'm going to go and show you what the solution is without using the power series. So once again, it should be relatively straightforward. Y double prime plus y equal to 0. That means d squared plus 1 of y equal to 0. That means our characteristic equation is r squared plus 1 equal to 0. R equal to plus or minus I. Therefore, our solution y would be equal to c sub 0 cosine x plus c sub 1 sine x. There you go. I think it took me exactly 20 seconds to do. That's pretty impressive. That's pretty cool. All right, so that's it. Okay, once again, this differential equation you will not use power series to do because it would take a way longer to try to come over the solution of this answer right here. But let me show you what to do, okay? So what if I do want to do power series solution? So, well, let's do the same thing like before. We're going to set up our power series solution. Let y equal to summation k from 0 to infinity c sub k x to the k. So that is what we're looking for. To put this solution into an actual answer, I need to find a way to represent c sub k. That's what we try to figure out. And that's what we're going to use a differential equation and all this power series to come over the answers. What do I need to do to plug in the power series into my differential equation? I need y double prime. So let's go for it. So to do y double prime, I do need y prime first. So if you remember, y prime actually equal to this, which when we reindex, it becomes this. So now I'm going to ask you to do is pause this video and go and try to see if we can figure out y double prime. Okay, I'll wait. Okay, well, I mean, I hope you pause the video, so I'm actually not going to wait. And if you think about it, just simply follow the pattern, you recognize that this is probably what it is. Oops. Because you differentiate twice. So differentiate first time is k x to k minus 1. Differentiate one more time, become k times k minus 1 x to the k minus 2. And you lose the first two terms, so therefore your summation will start at 2. But once again, we're going to reindex it. I'm going to reindex it to 0. And to do that, I'll have k plus 2, k plus 2, k plus 1, x to the k. Now, once again, if you don't want to deal with this process, you could simply memorize this is our y. This is our y prime. This is our y double prime. Now, but of course, in some cases, you might not have to reindex. So you should definitely have an idea as to how to play with the index a little bit. Okay, because in some problem, you might not actually adjust the index because of the way the equation is. And I'll show you what that is. Don't worry. But just not this example. So now I'm ready to rewrite my differential equation. So my differential equation is y double prime plus y equal to 0. That means is summation k from 0, k from 0 to infinity, c sub k plus 2 times k plus 2 times k plus 1, x to k, plus summation k from 0 to infinity, c sub k, x to k. And this whole thing equal to 0 because it's a homogeneous differential equation. So once again, I'm going to combine these two summations together. And then what I have is c sub k times k plus 2, c sub k plus 2 times k plus 2, k plus 1, plus c sub k, x to k, equal to 0. And once again, we are treating this equal to 0 as equal to 0 x sub 0 plus 0 x to the first plus 0 x to the second plus 0 x to the third plus dot dot dot. So therefore, every single coefficient is 0 no matter what k is. So therefore, allow me to form this equation. Once again, what we have is a recursive formula right here. That's what we're looking for. So now I'm going to rewrite this recursive formula into a nicer form. I'm going to define c sub k plus 2 to actually be equal to negative c sub k over k plus 2, k plus 1. Now this recursive formula actually will form two separate sequence. And why? Well, because we have a second order differential equation. And because of the fact that we have a second order differential equation, we should have two individual term. So two undetermined coefficients, c sub 0 and c sub 1, and which of course they will both be determined by initial condition. So now what I have to do is just simply figure out what happened to the rest of them. So if you think about it, c sub 0 will form the k to the 0 x to the 0 power term, which is the constant term. C sub 1 will form the x term. So maybe I should write this. So c sub 0, that would form our constant term. Wait, let me see. Okay, I wrote it backwards, so I'm going to do that. So for a constant term, we would have c sub 0. And for x term, we would have our c sub 1. So now the question is, what is x squared term? So x squared term will be here. And that will be looking for c sub 2. So c sub 2 would technically be meaning c sub 0 plus 2. So therefore become negative c sub 0 over 0 plus 2, which is 2, multiplied by 1. Which, if you think about it, that's just negative c sub 0 over 2 factorial. Then x to the third term. That will be c sub 3. And c sub 3 is actually c sub 1 plus 2. So therefore become negative c sub 1 over 1 plus 2, which is 3, times 2. So that you can think of as c sub 1 over 3 factorial. Now the x to the fourth term. X to the fourth term will be c sub 4, which is technically c sub 2 plus 2. So therefore will be negative c sub 2 over 2 times 2, which is 4 times 3. But notice, what is c sub 2? Is negative c sub 0, 2 factorial. So that means this is technically equal to and so it actually becomes positive c sub 0 over 4 factorial. And yes, hopefully you notice a pattern is emerging. But we're going to do a few more terms just to be sure. So what is this one? C sub 5. C sub 5 will be equal to negative c sub 3 over 5 times 4, which is basically negative 1 over 5 times 4, multiplied by negative c sub 1 over 3 factorial. So that becomes c sub 1 over 5 factorial. What do you think the next term going to be, which is x's sixth term? That will be c sub 6. And hopefully you will be able to tell me that that's negative c sub 0 over 6 factorial. And how about the seventh term, the x sub 7 term? That will be c sub 7, which is equal to negative c sub 1 over 7 factorial. And this pattern continue on forever. Now here comes the tricky part. How am I going to write out a formula for this? So if you notice, on the c sub 0 side, they all have c sub 0, but they are alternating sign from positive to negative, and we only have an even factorial on the bottom. So therefore, I'm going to say that this would define c sub 2k. Why 2k? Because 2k would only generate even terms. The term alternating start with positive to negative, so that means would be negative 1 to the k to begin. If it starts from negative term, it will be negative 1 to the k plus 1. It has c sub 0 on top. What's on the bottom? Notice that the factorial matches the subscript of c, which in this case 2k, so become 2k factorial. This formula defines all the even c sub k. Now onto the other side. The other side will be 2k plus 1. So once again, it starts with a positive term, then negative, then positive. So become negative 1 to the k. All of them have c sub 1 on the top. On the bottom is a factorial matches the subscript of c. So therefore will be 2k plus 1 factorial. So that form all the odd c sub k. So now I think we're ready to write out this power series. Our power series y would equal to summation k from 0 to infinity c sub k x to k. So which in this case just becomes c sub 0 plus c sub 1x plus c sub 2 would be right here. C sub 2 is negative c sub 0 over 2 factorial. So it becomes minus c sub 0 over 2 factorial x squared minus c sub 1 over 3 factorial x to the third. And then plus c sub 0 over 4 factorial x to the fourth plus c sub 1 over 5 factorial x to the fifth plus, well, actually it's minus the next term, but minus dot dot dot. You know what? I'm going to write out two more terms. Why not? C sub 0 over 6 factorial x to the 6 minus c sub 1 over 7 factorial x to the 7 plus dot dot dot. So notice that every single term either have a c sub 0 or c sub 1. So I'm going to separate them and therefore essentially kind of form two half series. C sub 0 minus c sub 0 over 2 factorial x squared plus c sub 0 over 4 factorial x to the fourth minus c sub 0 over 6 factorial x to the 6 plus dot 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 plus c sub 1x minus c sub 1 over 3 factorial x to the third plus c sub 1 over 5 factorial x to the fifth minus c sub 1 over 7 factorial x to the 7 plus dot dot dot. So hopefully you should see that I can pull out the c sub 0. And then what I have will just be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus dot 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 plus for c sub 1 I have x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x is 7 over 7 factorial plus dot dot dot. And hopefully you recognize that the first one is the cosine x power series. So therefore it's c sub 0 cosine x plus the second one is the power series for sine x. So therefore give us this nice and simple answers right here. Good so far? So, however, let's do a problem that's not as simple as this. So this next problem will probably not going to be able to wind up having some kind of nice, simple, closed form solution, a function form solution like this right here. But we can still generate the power series with a c sub k that we can actually define. So show you. So this one will be a little tougher because of, and I'll point out why. I have y double prime minus 2 xy plus y equal to 0. So this is definitely a lot harder problem because we cannot use characteristic root to come up with the solution here. And the problem is because we have an x in the middle term, we actually don't know how to do this equation. Because most of the equations that we have done so far are all constant coefficient differential equation. No matter what order it is, if it's constant coefficient, we can guarantee that I can use a characteristic root to come up with the solution. But now we have an x involved. Now that becomes a problem. So what I'm going to ask you to do is we're going to try to solve by using a power series solution. So show you what happened to this one. So because this one is a second, oh, I'm sorry, I forgot a prop. There you go. Because this one is a second derivative, so we just basically do the exact same thing we did. We're going to let y equal to summation k from 0 to infinity c sub k x to k. Okay? Y prime would equal to summation k from 1 to infinity c sub k times x to the negative 1. And remember, we can actually rewrite this one into by re-index it to y prime equal to summation k from 0 to infinity c sub k plus 1 times k plus 1 x to k. And y double prime would equal to summation k equal to 2 to infinity c sub k times k minus 1 x to the k minus 2. So that can equal to y double prime equal to summation k from 0 to infinity c sub k plus 2 k plus 2 times k plus 1 times x to the k. So those are our basic scenario. But here comes the issue. The issue is this x right there. That x messes up with our middle term. See, if I use my middle term as x to the k, when I plug into my differential equation, I actually have to multiply that by x, and therefore changes my exponent of x to the k. So the tricky part in this case is the following, is that when I take this equation, I will do the following. The y double prime, I'll keep it the same with the index re-index to be 0. But the middle term, I'm going to actually use my summation without re-index. And then my last term is just y, so therefore just plus our basic. And let that equal to 0. Okay? So now notice that if I multiply this x inside our summation, now allow me to now have our middle term to be x to the k. So that nicely solved that problem. If I did not do that, I will actually have a k plus 1 power in the middle, and that actually would screw up my problem. But now you might also notice an issue. The issue is my middle term is a summation that starts with 1, while my other two term has a summation that starts from 0. So how are we going to proceed with that? Well, actually simple. I would just simply pull out the 0 term from both the summation, first summation and last summation, and do the following. So this can actually equal to, I'm just going to plug in 0, so I get c sub 2 times 2 times 1 times x to 0 plus the summation k from 1 to infinity, c sub k plus 2, k plus 2, k plus 1, x to k. And same thing for this last term right here. I'm going to pull out the k is equal to 0 term. There will be c sub 0, x to the 0, plus summation, k equal to 1 to infinity, c sub k, x to the k. So now doing so would then allow me to rewrite my equation into this. Both of these are actually k x to the 0 power, so they're both constant term. So I would say is c sub 0 plus 2 c sub 2. That would be my constant term. And then plus summation k from 1 to infinity, c sub k plus 2 times k plus 2 times k plus 1 plus 2. I'm actually move the 2, or minus 2 actually, minus 2 c sub k times k plus c sub k. And this whole thing is multiplied by x to k, and that's equal to 0. All right, so now let's see how this works. So once again, because of the this is a homogeneous differential equation, therefore tell me that all the coefficient must equal to 0. And so in this case, it actually form two separate equations that we can use. The first one is this one. The second one is this one. So the first equation right here, this automatically tell me that c sub 2 is equal to negative c sub 0 over 2. Okay, so that gives us a relationship between c sub 0 and c sub 2 automatically, which is pretty cool. Because in this case, remember, we have a second degree differential equation, so therefore we should have c sub 0 and c sub 1 as the two beginning terms. Now what happened to this thing right here? So let's try to figure out this mess right here. So if I'm looking at this correctly, I can actually combine these two terms together into 2k minus 1, well, negative 2k plus 1. So if I move it to the other side, I will have c sub k plus 2 is equal to 2k minus 1 times c sub k. And then I have to divide it by k plus 2, k plus 1. So that form a recursive formula. So now I have this relation be between c sub 0 and c sub 2. And I have this equation relates c sub k and c sub k plus 2. Notice that it basically skipped every other term. That's the reason why we need two separate terms to begin. So we're going to go and start this process just like the last one that we did, which is like this right here. So I'm going to go and start with the constant term, which is c sub 0 once again. So the constant term. So that will give me c sub 0. X term, which would give me c sub 1. So what is the x squared term? The x squared term will be c sub 2, which we already know is negative c sub 0 over 2. What is the x to the third term? That would mean we have to find c sub 3, and that would be c sub 1 plus 2. So therefore k is 1 to use this formula. So it becomes 2 times 1 minus 1, which is 1, c sub 1, over 3 times 2. So once again, it shouldn't be too shocking to see that that just becomes 3 factorial. Well, actually, you know what? Let's not jump to conclusion. I'm going to just leave it at 3 times 2 for now and see what happens. And x to the fourth term. So that will be c sub 4. So we'll be using this formula again because this first formula only deals with 0 and c sub 0 and c sub 2. So c sub 4 will be c sub 2 plus 2. So k is 2. So 2 times 2 minus 1 is 3. C sub 2 over 4 times 3. So that come out to be negative 3 c sub 0 over 4 times 3 times 2 times 1. So I'm going to just say this is 4 factorial on the bottom for now. And let's hopefully the pattern hold true. X to the fifth term. That would mean you need to find c sub 5. That would equal to c sub 5 is c sub 3 plus 2. So k is 3. So 2 times 3 minus 1 is 5. And c sub 3 over 5 times 4. So that looked pretty good. So that become 5 over 5 times 4 multiplied by c1 over 3 times 2. So I think that's pretty much 5c1 over 5 factorial. And I know you might be tempted to cross out the 5, but I'm actually hesitant to do that. I'm going to keep it for now and see if I can actually form some kind of pattern first. So right now we did 4 terms. The first 2 terms doesn't count because they're given. So hopefully we can actually go through more term and hopefully we notice a pattern. C sub 6. So that would be c sub 4 plus 2. So 2 times 4 minus 1 is 7. 7 c sub 4 over 6 times 5. So therefore become negative 3 times 7 c sub 0 over 6 factorial. And x to the 7th term will be c sub 7. That would be 5 plus 2, so that would be 9 c sub 5 over 7 times 6. So that would actually come out to be 5 times 9 C1 over 7 times 6 times 5 factorial, so it's 7 factorial. So now I actually kind of notice a pattern now. Notice that the bottom just simply formed the factorial that matches the C sub whatever it is term in both cases, but the top have some kind of coefficient that constantly multiply. I'm going to do one more just to see if I can confirm my pattern. And I know my video is over 30 minutes, but I just want to finish up this example. So what is C sub 8? 8 would be 6 plus 2. So 2 times 6 minus 1 is 11. C sub 6 over 8 times 7. So therefore become negative. So these are actually all negative. Negative 3 times 7 times 11 C sub 0 over 8 factorial. And x to 9th term will be C sub 9. That's 7 plus 2. So 2 times 7 minus 1 is 13. C sub 7 over 9 times 8. So become 5 times 9 times 13 C1 over 9 factorial. So I noticed that I have a even power term, a even subscript term, and odd subscript term. The bottom factorial matches the subscript, but the top forms some kind of pattern. And as a matter of fact, if you look at the list of number, negative 3, negative 7, 3, 7, 11, it should not be too hard for you to figure out the next number, which 15 is because each one add by 4. And here is the same exact thing. It's 5 plus 4 is 9. 9 plus 4 is 13. So next number should be 17. So now comes the big question. How do I form this pattern? So actually it will be this. C to 2k would be something C sub 0 with a 2k factorial. I just have to show the numerator. So the numerator would actually be this. I'm actually going to have to write out this way. So I'm going to show you how to write out. 3 times 7 times 11 times dot. Maybe I'd use parentheses. How's that? And the term here is actually 4k minus 3. And then times C sub 0. Actually 4k minus 5. Because our first term is actually negative 1. So if I plug in 1 for k, that would be 4 minus 5, which is negative 1. Remember, our index starts with 1. And maybe I'll write it this way. There you go. Because it would actually end at the 4k minus 5 term. So for 8, it would be 2 times 4. So 4 times 4 minus 5 is 11. There you go. Now for the 2k plus 1 term, it will actually be this. So once again, it will start with actually start with 1, which is this one right here, 1. And this one actually is a negative 1, C sub 0. So I will actually have 1 times 5, times 9, times 13, dot. So this one would be 4k minus 3, because it's just basically the same exact pattern, except I need the first number to be 1 instead of negative 1. So minus 5 will give me negative 1, but minus 3 will give me positive 1, because 4 times 1 minus 3 is positive 1. Over 2k plus 1 factorial C sub 1. So therefore, in this case, our solution would be this. Our solution y would actually equal to this thing. C sub 0 plus C sub 1x plus summation k from 1 to infinity. C sub 2k, so it will be negative 1 times 3 times 7 dot times 4k minus 5 over 2k factorial x to the 2k with a C sub 0 outside plus C sub 1 on the outside, summation k from 1 to infinity, 1 times 5 times 9 dot times 4k minus 3 over 2k plus 1 factorial x to the 2k plus 1. So this would form our solution to this differential equation. And notice that this solution doesn't actually turn into any kind of closed off simple form. Okay? Alright, I know my video is a little long, so I'm going to stop right here and we'll continue on the next video. Alright, talk to you guys later. Bye-bye.